Welcome back. It's time for Chapter 12, Laplace. So I'm going to just go over the scribbly notes, and these are posted if you'd like to pull them up, print them out, or whatever you'd like to do and follow along. Okay, so Chapter 12, Laplace. So why do we have this thing? Well, if you remember back in Chapter 8, we derived a differential equation for a parallel RLC circuit. And that was just one equation. And then when we were dealing with mutual inductance, we played with a few others, but we have to treat them all independently because we don't have a way to simultaneously deal with multiple equations. Well, Laplace will let us deal with multiple linear differential equations. That's one reason. The second reason is we can handle transient responses better than we did in Chapter 7. If you remember, Chapter 7 was step responses, where you'd have a switch that would open and close, and you'd see the signals decay or go up to a new signal. So that was kind of a simple response, but we can handle a little more complicated things than that with Laplace. Also, we can handle steady-state sinusoidal response when the frequency is varied. So that seems a little contradictory. What we're talking about is the frequency will change, and then after some small amount of time, the sinusoidal signals will stabilize. And we can model that. Like in Chapter 9, all of the phasors that we used, frequency was held as a constant. But with Laplace, we can vary the frequency, and we can see when the circuits are stable, what is the effect of frequency. And that sort of leads into something called transfer functions, which is a ratio of input to output, and that lets us build frequency filters and things like that. Okay, so these are kind of some three specific reasons why we're dealing with Laplace. But generally speaking, what we're really trying to do is just, broaden your brain, and this is just another tool to help you understand circuits altogether, all right? So it's also, Chapter 12 is also fundamental to the remaining chapters in the book. Okay, so it gets a little freaky. When I look at this stuff, I really admire the geniuses that have walked this earth, like Laplace and Euler and Newton and these guys that just amazing stuff that they figured out. But anyway, so we have to take this a little bit on faith, right? That this stuff works. And even if you take a lot of the math classes where these tools are rigorously developed, even then, there's a lot of faith involved in just accepting that these things work. Anyway, so given a time domain function, f of t, so little f of t, so this is what we've been dealing with so far this semester, with the exception of phasors, where we got into frequency domain. But given a time domain function, we can define the frequency domain function, capital F of s, using a Laplace transform. So big F of s is the Laplace of little f of t, and it's defined by this integral from 0 to t of f of t times e to the minus st dt. And it's just this wacky thing. So the input is f of t, which is a function of time, and then the output is going to be big F of s, which s has units of 1 over time or frequency. So basically what a Laplace transform is doing is transforming a problem from the time domain, little f of t functions, into the frequency domain, big F of s functions. But it does this more flexibly than phasors, all right? Phasors back in Chapter 9 were limited to steady state, single frequency sinusoidal functions where the frequency is constant and everything's an AC signal. Here we can model not only varying frequencies in AC signals, but we can model more complicated transient inputs like steps and impulses and things like that. So it's a more powerful, more generalized frequency domain analysis method. All right, in a nutshell, kind of what we're going to do is we're going to start with a f of t, little f of t, time domain functions. We're going to do this Laplace transforms into the big F of S frequency domain. We're going to do some algebra on that and get some more big F of S frequency domain. And then the very last thing we'll do is we'll translate back to the time domain. So there's pros and cons with Laplace. The pro, you can consider it a pro or a benefit that the algebra in the F domain can be easier than dealing with integral differential operations. If you remember in chapter 8, when we were dealing with the response of a parallel RLC circuit, we were dealing with integrals and derivatives, and it's not pretty. It's not easy to do that. In fact, it's just about impossible when those things get much more complicated than they were in that problem. Okay, so an advantage of Laplace F domain stuff is we're just going to do algebra instead of integral differential operations, and that's easier. Okay, a con is it only works if RLC constants are known. All right, so you have to plug those values in, and then you get a set of equations that only works for those values. All right, if you change the RL or C constants, you have to start over. It breaks all the math. That could be considered a con. If you remember in chapter 8, we played with those values. That is, in chapter 8, we got an integral differential equation, and then we adjusted R to get, say, critical damping or something, right? Capital R was a variable. Okay, you can't do that in these things in Laplace domain. All right. So there's two functions that are introduced. These turn out to be probably more important later on in the book, but they're introduced here. Something called the step function, which is symbolized by some constant k times u of t, and it just looks like this. It's 0 before 0 time, and it's 1. Well, u of t is 1 after 0, and if you multiply the whole thing times a constant, then you get k u of t. But u of t is 0 to 1. And so basically, this can be used like a switch, where the signal is 1 after 0. Pretty simple, really. And then there's this k delta t, or the impulse function. And this is a function that has 0 width and infinite height, but it has constant area k. It's one of those calculus things where the derivation where the width shrinks slowly, and then as the length approach, and then the width is shrinking and the height is growing, but the area is staying constant. It's one of those freaky calculus things. But we can use it to interject a glitch in the matrix, so to speak, like a pulse of current or a pulse of voltage or something. We can use it to model that. But as far as the constant area thing, that's what this integral is saying. So if you integrate k delta t from minus infinity to infinity, you just get k, which just means that k is the area or strength of the impulse. It has constant area, but infinite height and 0 width. Anyway, so these can be used to model switches. The step can be used to model switches, and the impulse can be used to model glitches, like transient pulses of things from inductors getting switched in and out of the circuit, and things like that, things that are impulsive. And it can be used for fancier things than that, but switches and glitches are two of the easiest to understand things. All right, what we're going to do here, well, let's get into some Laplace transform. So Laplace transform is defined by geniuses Laplace and all the guys that came before him, they came up with this thing. Now, if you apply this integral to various functions of t, you'll get Laplace transfers forms for that little f of t, all right? So you plug in different little f of t's into this thing and you get big f of s's. So for example, you could plug in the step function. Step function is a function of time. It's 0 before 0 time, and then it steps up to 1. So that's a function of time. So if we can calculate the Laplace transform of the step function just by putting it into the defining integral. Right? This integral right here is the definition of Laplace. So big f of s will be this big integral here, f of t to the minus st dt, where f of t is the step function. Okay, the step function is 1 after 0, and we're only integrated from 0 to infinity. So we can just use 1. Right, the value of the step function is 1 from 0 to infinity. So you put that in there and you get, and do the integration and plug in the limits of integration, you get 1 over s. So what we're saying is the time domain function signified by little f of t has a certain frequency domain function signified by big F of s. So the step function u of t, which is a function of time, has this Laplace transform 1 over s. Or just in plain English, 1 over s is the Laplace transform of u of t. Okay, and you can plug in all kinds of functions of t, t squared, cosine t, 2t plus 3t squared, whatever you want, all kinds of functions of t. Do this integral and you'll get some big f of s. Okay, the common ones have been done for us. This is not a math class, it's an engineering class. We just want the answers. So people have taken, and I'm going to make you do a couple just so you get the feel of these, but people have taken various functions of time, so little f of t's, like the impulse function, the step function. Here's t, just a 45-degree line, t squared, e to the minus at, cosine omega t, various functions of time, and run them through this defining integral here and come up with these big f of s's, all right? So delta t will be 1, and you could perform that integration and see or read the book. T, if you stick this t into that integral, you get 1 over s squared. If you stick e to the minus at into that integral, you get 1 over s plus a, like that. And there's lots more of these, okay? So in summary, we call these functional transforms, in that they take a function of time and turn it into a function of frequency. So they transform functions of time, little f of t, to functions of frequency, big F of s. And there's a table in the book, table 12.1, that defines many common Laplace transforms. So I'm going to make you do a couple of Laplace transforms by doing these integrals, but just to help you remember this definition, my attitude is, we're engineers, we just want to get something working, and we'll leave it to the mathematicians to provide most of those tools, but still we need to understand this fairly well. All right, so we call these functional transforms. All right, there's also something called operational transforms. An operation is something like multiplication or derivative or integration or time shifting, things like that. So, for example, what happens if you multiply a constant times little f of t? And there's a proof in the book that will tell you that that's the same as multiplying that same constant times the big F of s. So you constants just carry through is kind of what that's saying. And then for another one, what would happen if you took the derivative of little f of t, what would that do to the frequency domain version, big F of s? How would that change? So, and this is derived in the text, but basically they're saying that the derivative of little f of t in the time domain is going to be this thing, s times big F of s minus little f, or the time domain value evaluated at 0 minus. Okay, so before the y-axis, because this is what we're doing is a one-sided Laplace. It only applies from 0 to infinity. It doesn't apply for negative time. And I'm not a mathematician. I can't really elaborate on why that is the case, but sometimes you got to watch this 0 minus thing. What if you wanted to go backwards? So what we just did was going from time domain to frequency domain. What if you wanted to go from frequency domain to time domain? Then here's one that's saying, what if we took the derivative with respect to s of some frequency domain function, big F of s? What would that do in the time domain? And that's equivalent to just multiplying times t in the time domain. Like that. And there's many more. So this is table 12.2 in the text. And yeah. Okay. So that's that. Okay, what are we going to do, right? Besides, I'm going to have you derive some functional transforms and then play with one or two, not much, but just one or two of these guys and then one or two of these operational guys, just to get a hang of this, a little bit of a hang of this stuff. But what are we going to do mostly in this class, all right? So I made a little cartoon here of how the workflow is going to go. All right, so applying Laplace to circuit analysis. Well, we're going to start with a bunch of circuit elements, right? Inductors, resistors, capacitors, sources, with known constants, right? Known RLC values, and sometimes known other values too, but known constants. Basically, that means you can't change them once you've derived the math. That the expression you get only works for the initial constants that you solve it for. It's just the way the method works. Anyway, you start with those. You do a bunch of you apply the time domain definitions like V equals Li, Li prime, I equals CV prime, V equals IR, KCL, all of these time domain rules, and you get an integral differential equation, right? An equation with derivatives, constants, integrals, crazy stuff like that, right? But it's a function of time. Then you apply the functional transforms in this table right here, right? You get these time domain equations. You'll apply these transforms in this table, and you'll turn these functions of time into functions of frequency. So now we've moved from the time domain to the Laplace domain, or the time domain to the frequency domain. So up here we have integral differential stuff. We have integrals and derivatives. Down here we just have algebra. Okay, which most of the time is easier than derivatives and integrals. So you got a bunch of algebra with big capital letters, right? Right down in here we're little f of t on these guys. And then up here and here we're big F of s, except instead of little f we have little v and little I, and then instead of big F we have big V and big I. Okay. Then you do some more algebra and you're going to end up with what's called a proper rational function of s. So a rational function is a function that's expressed as a fraction, a ratio, has a numerator and a denominator, And the numerator and denominator are polynomials of descending exponential order. And then a proper rational function means the denominator has a higher order than the numerator. Okay, some of these details won't matter because we're not going to see problems that are not okay for us to solve, at least not in this class, but in real life you might, maybe. Anyway, you get this, where are we? So you're going to get some proper rational functions of S, then you're going to do what's called a partial fraction expansion. Okay, because, or a PFE, you do a partial fraction expansion, you end up with a partial fraction expression. And those, you can inverse the plus. Inverse the plus from the frequency domain back to the time domain. That's why we need to do a partial fraction expansion, because we need expressions that look like this. Because if they look like this, we can go back from the frequency domain to the time domain. All right? That's what we're going to do. So what I've done is, well, I have to just work some problems for you to see how this flowchart works. But what I've done to explain this partial fraction expansion thing, I made a little flowchart or a little example. Rather than, in math terms, rather than talk about this in abstract symbolic math terms, I just made an example. So assume this is a proper, this guy here, big F of S, is a proper rational function. So it's a rational function because it has a numerator and a denominator. It's a ratio. And it's proper because the denominator, the highest S term, is squared. And here in the numerator, the highest S term is just S to the 1. So the biggest exponent on the denominator is bigger than any exponent in the numerator. So the denominator has a bigger power, is the simple way to say that. So that's called a proper rational function. Well, so most of the problems in the book they're going to be fine. You don't have to worry about whether they're proper or not. But anyway, the point is, after you do a bunch of algebra in the frequency domain, you're going to end up with an expression that looks like this. Okay, and if you don't, you're going to make it look like this. Okay, you're going to make it look like a proper rational function, because if you get it to look like a proper rational function, you can do what's called a partial fraction expansion. Right, so I just made one up. So that's this thing. So I made up s plus 1 over s squared plus 5s plus 6. I just made that up. You can factor the bottom. It's a quadratic. Right, and the roots are s plus 3 and s plus 2. Okay, so this is just f of s here. This right here, this is just f of s expressed with the fully factored denominator. So that's what you do. You fully factor the denominator and make it look like these little things. And then you can do this. This is just kind of a straight algebra technique. It's just this thing that kind of hung out in math. Nobody cared until it turns out you can use it on this Laplace junk. But it's just an algebra thing. It's not specific to circuits or even Laplace for that matter, but it is useful to Laplace. So if you have one of these things here, you can do this. So this is an identity symbol right here, which means that this expression on the left of this identity has to be identical to the stuff on the right. That means that they need to produce the same results for all values of x, or in this case s. Let me give you an example of what's something that's not an identity. Like 2x equals x squared. That's not an identity, because if if x equals 2, you get you get 4 and 4. That's cool. But if if x equals 3, you get 6 and 9, which is not equal to 9. So this is not an identity. An identity, the left-hand side and the right-hand side have to produce the same result for all values of s. Once again, that kind of mathy precision or whatever, we don't need to worry about it. We just need to follow the method and turn the crank. So what you do is you take you're going to end up with one of these after doing the algebra in the frequency domain. And you're going to break it apart into these two doohickeys. And then you need to solve for the k1s and the k2s. And the way that you do that is you multiply through by the denominator of each constant, right? You multiply through by the denominator of each constant. So you multiply through, to get k1, you multiply through by s plus 2. That's the denominator of k1, of the term with k1 in it. You multiply through. So if you multiply through this whole thing by s plus 2, then the s plus 2 on this side will cancel. And the s plus 2 in the numerator up here will cancel, and you'll just get k1. And then there'll be an s plus 2 up here in the numerator. But the next thing you do is you evaluate when s equals minus 2. And if you imagine there's an s plus 2 here, when you put in a minus 2, this becomes 0. So in effect, you just end up with this thing here. You just end up with s1 over s3 equals k1, and you evaluate at s equals minus 2. Okay, I'll have some more examples of this, but this is just kind of a shorthand way to explain these partial fractions. So you put in the minus 2 and you get minus 1 over 1, which is 1. So k1 is 1. Okay, then you do the same thing for k2. That is, to solve for k2, you multiply through this whole expression by s plus 3. So there'll be s plus 3 on the top, and those will cancel, and you'll just get k2. There'll be s plus 3 on the top here, and that'll cancel, and you'll get s plus 1 over s plus 2. There'll be an s plus 3 in the numerator up in here, but you're going to evaluate at s equals minus 3, and then that'll make that s plus 3, it'll make that 0, which will eliminate the k1 term. So you end up with k2 equal to this junk, evaluated at minus 3. You plug in the minus 3's, you get so you plug in the minus 3, you get a minus 2. Plug in the minus 3 here, you get a minus 1, so you get 2. So so k1 is 1 and k2 is 2. So you plug that back into the original identity up here, and our expression f of s, which was originally this, plugging in the k's into our partial fraction expansion gives you, there's the 2 and there's the 1, gives you this. So what we're saying is this stuff here is identical to this stuff here. All right? And this stuff here in the box, the 2 over s plus 3 and the 1 over s plus 2, that can be turned back into time domain, right? S plus a, it's e to the at, right? We can go back to time domain. That's the whole point of doing this partial fraction expansion. So, yeah, and then just to check, a little check to see if this stuff, if this stuff here is in fact equal to this stuff here, just throw in some numbers. So I used my favorite number, 42. So if you put 42s in here, you get 43 over 44 times 45, and you get 2 over 45 minus 1 over 44. Works out to 0.217 on the left and 0.217 on the right. So it works for 42. And you could try a couple more numbers and until you feel confident that it's actually working. All right. That's what we're going to do. We're going to, let me just summarize here. We're going to start with, time domain with known constants. Apply our time domain rules, get these time domain expressions, Laplace them into the frequency domain, fiddle around with them, do whatever we need. We'll end up with a proper rational function. And then we need to go back to time domain. So what we'll do is we'll do a partial fraction expansion. We'll get a partial fraction expression, and that partial fraction expression can be converted back to the Laplace domain and back to time domain, and we'll end up with time domain functions that typically they're just signal response curves, like, right? There's no integrals or derivatives in them. They're just time domain signals that are just showing what the V's and the I's are doing with time. That's what we're interested in, not so much the derivatives and integrals. Okay, and biggest part of the algebra is this PFE business, which I'm trying to explain down here. All right, I'm going to go through, I'll have a couple more videos where I'll talk about how to calculate Laplace transforms, a little bit about playing with operational transforms, and then we'll do a circuit where we start with a circuit and go all the way through this process and then back to the time domain. Okay? Thanks.